This is Lesson 7, Complex Numbers. Let's start by talking about the imaginary number I. If we had the equation x squared equals minus 1, and we would try to solve this equation for x, we would find that we would have no real solution. Because if x squared equals minus 1, that means x equals the square root of minus 1. The square root of minus 1 is not a real number. There is no real number solution for that. As a result, it was necessary to invent a new number, and this became the imaginary number I. So this new number I became equal to the square root of minus 1. So how do I perform operations using imaginary numbers such as I? Well, let's look at a few examples. Let's say I want to simplify the square root of minus 5. How would I go about doing that? So initially, let's say if we got the square root of minus 5, that's equal to the square root of minus 1 times the square root of 5. Well, square root of 5 is a real number, but what's the square root of minus 1 equal to? So our answer, therefore, would become I times the square root of 5. So here's a perfect example of how we can take a square root of a negative number and simplify it to being a real number times I. Let's look at some other examples. Let's say I had the square root of minus 25. Again, following the same procedure we used in the previous example, let's see what we get. This would equal the square root of minus 1 times the square root of 25, which can be further simplified to become 5i. Now let's look at one last example involving simplification. Let's say we had the square root of minus 75. How could we simplify that? That would become the square root of minus 1 times the square root of 25 times the square root of 3. And this would yield a final result of 5i times the square root of times the square root of positive 3. So square root of minus 75 simplified as 5i times the square root of 3. Now let's look at some more examples involving mathematical operations. Let's say I had 3i plus 4i. That would simply equal 7i. We add the coefficients 3 plus 4, and we keep the imaginary number I. So 3i plus 4i is 7i. Similarly, how would I handle I times the square root of 2 plus I times the square root of 3? That would simply equal I times the quantity square root of 2 plus the square root of 3. Now similar rules would apply if we were subtracting rather than adding. Now what about multiplication? What if I had 3i times 2i? That would equal 6i squared. Well, what is I squared? I squared But 6i squared would simply equal 6 times I, or 6 times the square root of 1 times the square root of 1, which finally would equal minus 6. Now, this brings up an interesting point on what I squared is equal to. We know that I equals the square root of minus 1. Then I squared would equal minus 1. I to the third would equal minus 1, and finally I to the fourth would equal positive 1. Now this pattern would repeat itself in that I to the fifth would equal the square root of minus 1, I to the sixth would equal minus 1, I to the seventh would equal minus I, and I to the eighth would equal plus 1. So this pattern repeats every 4. So now let's look at one last example here in this series of examples. Let's say I had 3 divided by I, or 3 over I. Well, first of all, it's considered non-standard to have an imaginary number in the denominator of a fraction. So we must get rid of that. And the way we get rid of it is we simply multiply by I over I. So let's look at what happens here. Now this would yield 3i over I squared. But let's look at our previous list that we created here, right here. And remember what I squared was equal to? I squared was simply equal to -1. So our final result would simply be minus 3i. So here we have seen examples of how we add, subtract, multiply, and divide imaginary numbers. Now let's move on to complex numbers. A complex number is a number that's written in the form a plus bi, where a is the real part and bi is the imaginary part. Both a and b are real numbers, and I is obviously imaginary, and so a complex number, therefore, is any number that can be written in the form a plus bi. Now, one thing that we need to remember is that any number can be written in the form a plus bi. A purely real number would be written a plus bi and b would be 0, okay? So a pure real number, b would be 0. A pure imaginary number, a would be 0. Or a complex number where you've got a real part and an imaginary part is a plus bi, where neither a nor b is equal to 0. Now let's look and see what happens when we add 2 complex numbers, or figure out what the sum of 2 complex numbers. So let's say we have 2 complex numbers, a plus bi plus c plus di. What would our sum be equal to? We would obtain our sum by simply adding the real parts, a plus c, and then adding the imaginary parts, b plus d. So a plus bi plus c plus di would simply equal a plus c plus the quantity b plus d, I. And if I were to use numbers, say I had 3 plus 2i plus 4 plus 3i, we'd add the real parts, 3 plus 4, that would give me 7. Then add the imaginary parts, 2i plus 3i would give me 5i, or my result would simply be 7 plus 5i. So now, what would we do if we were to multiply complex numbers and look for a product? So let's say we had a plus bi times c plus di. Well, in this case, basically you're going to follow the same rules you followed when you did FOILing. Remember, first, outside, inside, last? That's exactly what you're going to do here. So your result would simply be, we take the first terms, the a and the c, we'd multiply those together, we'd get ac. The first terms, outside terms, we'd multiply the a and the d. Okay, that would give me ADI. So first, outside, inside, C times B, and last, B times D. But notice, when we're doing the last terms, it's BI times DI. So therefore it's BD I squared. Now, remember back previously in this lesson, what is I squared equal to? I squared is simply equal to -1. So our final result would look like this. AC minus BD, that quantity, would be the real part, plus AD plus BC quantity times I. And again, if we were to use actual numbers and multiply 3 plus 2i times 4 plus 3i, our result would be 6 plus 17i. The way we get this is we would simply, again, multiply the 3 times 4, which gives me 12. Then I would subtract the 2 times 3, which is 6. That'll give me 12 minus 6, or 6. Then I would take the 3 times 4, I'm sorry, 3 times 3, which is 9, and 2 times 4, which is 8. 9 plus 8 is 17, which gives me my final result of 6 plus 17i. So now the last thing we want to talk about is the division of complex numbers. So let's say we had 5 minus I divided by 2 plus 3i. Again, remember that I is non-standard in the denominator, so I must get rid of it. So basically what I'm going to end up doing is multiplying by something referred to as the conjugate. So I would take my original expression, 5 minus I over 2 plus 3i, and I would multiply it by 2 minus 3i over 2 minus 3i. And once we'd FOIL the numerator and FOIL the denominator, our result would be, for the numerator, 7 minus 17i, and for the denominator it would be 13. Well, you can leave your answer this way, or if you want to write it strictly in the form a plus bi, then it would look like this. 7 over 13 minus 17 over 13i. So here you would have exactly what you'd expect, in that you would have a real part, the 7 over 13, and an imaginary part, minus 17 over 13i. Now this concludes our lesson on imaginary and complex numbers. So now proceed to try the worksheet and see whether you understand this material or not.